I want to pick up where we left off in the previous video with our discussion of the um, rigid rotor rotational vibrational system, and we had worked out this as the Schrodinger equation for that system, where we've got our kinetic energy operator here, and we assume that the potential energy of rotation is zero. And we've, based on a two-dimensional rotation, if we assume a constant r and force two-dimensional, then we're only interested in one angle about which this thing will be rotating. Now, as it turns out, the equation, the function that satisfies this particularly well has the same form as the function that satisfied the free particle that we solved in chapter 4. And so we've got what we're going to call a phi plus and a phi minus that refers to clockwise and counterclockwise rotation. And then we've got this exponential, I times the quantum number times the variable. But this variable is an angle rather than a position variable, so that makes the calculus slightly different. And so when we meet in class, we'll solve as an example for the normalization constants for these two wave functions. But the next thing that we want to discuss for ourselves is, what is this quantization variable? What is m sub L? In order to avoid the probability density having multiple values at the same position, the particle has to be indistinguishable after each full rotation. So that what we're saying here is that this function at any particular position has to be the same as that function at that position plus 2 pi. So if we take the system that we have and substitute in phi plus 2 pi for phi and set those equal to each other, the only way that will work is if if we divide both sides by this term, we get e to the 2 pi I m sub L equals 1, and then using Euler's relation, we get cosine of 2 pi m sub L plus I sine 2 pi m sub L is 1. The only way that is going to work, the only set of numbers that satisfy that, and you can try this out on a calculator to make sure I'm right, but the only set of quantum numbers that's going to work on that would be 0, plus or minus 1, plus or minus 2, etc. Basically positive, negative integers, and 0. And since those are the only possible values that can work in this equation, that introduces quantization to the solution, to the wave function. Now, if we apply the Hamiltonian operator to this system, we get an energy that's equal to h bar squared times m sub L squared over 2 times reduced mass times the bond distance squared. And we can look at reduced mass times r squared as the moment of inertia for the rotation. If we apply the angular momentum operator, which is IH d phi, we get, and I'll show you what we mean here, IH d phi, we pull out the normalization constant, we take the derivative here, so the derivative of e to the im phi is e to the im phi times im, and we've already got negative I out here, so now our setup is m sub L times h bar times e to the im sub L phi, and that gives us m sub L times h bar times the original equation. So that is our, I'm sorry, times the original function. So there is our eigenvalue. Substituting that into the energy expression, we can say that the energy of rotation is the angular momentum about the z-axis squared over 2 times the moment of inertia. That's the same result we get in classical mechanics, just with angular momentum and energy both quantized according to m sub l. Now, the position operator phi does not commute with the angular momentum operator L sub z, just like the position operator and the momentum operator didn't commute in the translational case. So that means that we cannot know the position of the particle in its rotation, only the probability of finding it in a particular area. But one thing to notice is that the number of nodes per rotation, per 360-degree rotation, is going to be 2 times m sub l, 2 times the absolute value of m sub l. Now the math is going to get slightly more complicated for us when we move to 3 dimensions, because we're going to have a second angle variable, but we'll still assume that the bond length stays constant. And so when we add in that third dimension of rotation, that second variable of angle of rotation, and again, the conversion to spherical polar coordinates makes the Hamiltonian a little bit more complicated. So we get h bar squared over 2 times the moment of inertia, times 1 over sine of theta, that's the new angle of rotation that's being introduced, times d theta of sine times d, the wave function, so this will be our 3-dimensional rotation wave function, plus 1 over sine squared theta d2 d phi of that wave function will give us the energy of rotation. Alright, so here's that equation again, and again what we mean here is r is going to be the distance from, basically the bond distance, distance from the center of mass of the molecule out to the edge of the rotation, and then we have angle from the z-axis and angle around the xy plane defined by phi and theta. So what does that function look like that we called y? We're calling our wave function y now when we talk about 3-dimensional rotation instead of phi. Phi was the wave function when the rotation only depended on one rotational angle, and instead of psi, which you guys like to refer to as pitchfork or trident, when we talked about translational motion. But to make our math a little bit easier, we're going to call beta 2 times the moment of inertia times the energy over h bar squared. And the reason why we can, that makes it convenient for us to do that, is we rearrange the Schrodinger equation. We move this whole term to the other side, and basically now we have beta sitting here. So negative beta times this is the wave function. So now we've got a little bit less complicated math to do, not a lot less, but a little bit less. Now if we multiply both sides by sine squared theta, that takes the sine squared theta out of here, and it takes the 1 over sine theta and turns that to sine theta. And then we'll subtract this from both sides and add this to both sides to get these terms separated from one another. So now we've got y has to be a function who the negative of its second derivative equals this expression as we've got it shown here. And I know this looks cumbersome, but look at what is convenient about this the way it's written. There's no derivative on this term. On this term, the derivative is with respect to phi. All the derivatives on the left are with respect to theta. So we've got, for all intents and purposes, our variables separated. And that means that y has to be a function that has separated variables, where it's a product of two functions. One depends on one angular variable and the other one depends on the other angular variable. And these are special functions that come up quite a bit in mathematics and physics. We call them spherical harmonics, and we'll discuss their form in a little while. But if we substitute this expression into the equation above and then divide through by these two, look at what happens. On this side, if we're taking second derivative of the full function, we can pull the phi terms out. I'm sorry, we can pull the theta terms out to the front, and then when we divide through by the full function, we get 1 over phi there. So now we have only phi on the right. And then something analogous, I'll get you to check my math for me on this to make sure, but something analogous happens here when we pull out the what is going to be constant, the phi term, out to the front, and then divide both sides through by the full function. We get 1 over theta. So the entire left side of the equation now depends only on theta. The entire right side depends only on phi. And look at the right side of the equation and see, go back to previous slides, previous videos, and see how that reminds you of the setup on the particle in two-dimensional ring, the two-dimensional rotation case. All right, now look at what happens here mathematically. If we use the function that we talked about for the phi case, for phi here, the derivative of that is I m sub l times the original function. So the second derivative is negative m squared, m sub l squared times the original function. So if we divide through by negative 1 over phi, we get this side of the equation is just m sub l squared. So now we've solved this equation for an expression that relates only to theta and m sub l squared. Now we can use that result to find eigenfunctions that satisfy theta with the boundary conditions that the total wave function, theta times phi, the y wave function, has to be single valued for theta and phi, and that the amplitude of these functions is always finite. And that would take us a little while mathematically. But the results come out that the beta term that we defined earlier has to be L times L plus 1, where L can be anything from 0 up to integers, and then m sub l is defined as having to be a whole number between negative L and positive L. So what we've just basically derived is a lot of the quantum numbers that you're used to hearing about in general chemistry for electronic situations. We've derived them for rotational spectroscopy and derived why those quantum numbers are the way they are. So y, the wave function for three-dimensional rotation, is going to depend on two quantum numbers, L and m sub l, and it's going to be separatable into two wave functions, one depending on theta, the other depending on phi. Theta's wave function depending on two quantum numbers, and phi depending on only one of those quantum numbers. And in the next video, the final video for this chapter, we'll go ahead and look at energy and momentum and the other calculations that we can do using this wave function.